Good morning everyone, I am P. Mahendra from CSE Department B section. Today I am going to explain stability analysis of an equilibrium points in nonlinear pendulum systems using phase plane methods. And my guided faculty was Mr. G. Satyanarayana sir. Introduction. Nonlinear pendulum systems are governed by nonlinear differential equations. Stability analysis helps understand how the system behaves near equilibrium points. Phase plane methods provide a graphical way to study them. Study system dynamics. Used in physics, engineering, and mathematical modeling. Phase plane methods provide graphical way to study system dynamics. Next, mathematical model of a pendulum. Angle theta. Equation of the motion without damping. Theta plus g by L sin theta is equal to 0. A second order nonlinear differential equation in matrix form. Convert to first order state system. Converting to state variables. Let x1 is equal to theta, x1 is equal to 0 into 1 is equal to 0, x2 is equal to theta, x2 is equal to 0 into 2 is equal to theta. Then the system becomes x into 2 is equal to x2 into dash 1 is equal to x minus 2 into 1 is equal to into 2, x into 2 is equal to minus g by L sin theta into f1 is equal to g by minus g by L sin theta by sin theta x theta into 2 is equal to minus g by L sin theta into 1 x1 sin into x1. This forms of a system of nonlinear equations suitable for phase plane analysis. Next, matrix representation. Here you can see the matrix representation of a state space form. It is obtained from using Jacobian matrix and used for stability analysis around equilibrium points. Equilibrium points occurs when theta is equal to 0 into theta is equal to 0 into theta is equal to 0. So sin theta is equal to 0 by sin theta is equal to 0 into sin theta is equal to 0. Equilibrium points. Theta is equal to 0, pi, 2 pi, and so on 0, and so on. Theta is equal to 0, pi, 2 pi is equal to 0, theta is equal to 0, pi, 2 pi, and so on. Corresponded to stable and unstable positions, corresponded to state position and of the equilibrium pendulum. Types of equilibrium. Types of equilibrium. First one, theta is equal to 0, downward position, stable. Second one, theta is equal to pi, upward position, unstable. Means theta is equal to 0. There is no downward and it is in the downward position. So it is unstable. 0 theta is equal to pi, upward position, unstable. It is an unstable, represented at 2 pi and 3 pi. Due to periodic motion, matrices and calculus helps classify stability at these points. Linearization around equilibrium. Use Taylor series to linearize near equilibrium. Replace sin theta is equal to theta for small angles. Linear system becomes theta plus g by L into theta is equal to 0. Leads to harmonic oscillator equation. Next, we are going to see Jacobian matrix for stability. Jacobian of system. J is equal to 1 minus GL cos theta into 0. J is equal to being B matrix 0 and 1. Fraction G is equal to cos theta and 0. And matrix by G is equal to evaluate for each equilibrium. At theta is equal to 0, cos theta is equal to 1. At theta is equal to pi, cos theta is equal to 1. And we can represent that as in the equilibrium state J is equal to 0 minus Lg cos theta 1 into 1 0. Evaluate for each equilibrium point. And we can see the matrix of stability in a Jacobian matrix for stability. This is the form of Jacobian matrix for stability. Next, we are going to see eigenvalues analysis. Coming to eigenvalue analysis. For theta is equal to 0, lambda is equal to plus or minus Ig by L lambda is equal to PMISQRT G by L. Lambda is equal to plus or minus Ig by L pure imaginary center type K stable. For theta is equal to pi, lambda is equal to plus or minus G by L, L lambda is equal to PM SQRT G by L, lambda is equal to plus or minus G by L. One positive eigenvalue is unstable saddle point. Here in the one positive eigenvalue is unstable and saddle point. Matrices plus eigenvalues is equal to classify stability. It classifies stability. Matrices and eigenvectors are both combined to classify and stability and it is also eigenvalue is unstable and saddle. Here you can see the how we can write the eigenvalues analysis. Next we are going to see phase plane concepts. Phase plane concepts are nothing but graph of theta versus theta dash. Show trajectories of the pendulum and helps visualize stability circles around stable equilibrium, hyperbolic curves near unstable equilibrium, and nonlinear system reveals richer dynamics. Means it shows in the concepts are phase plane concepts are graph of theta versus theta shows trajectories of the pendulum, helps visualize stability, circles around stable equilibrium, hyperbolic curves near stable equilibrium. Nonlinear system reveals richer dynamics. Next, phase plane of non-pendulum. Key features: closed orbits around theta is equal to 0 stable. Subtrix, separatrix, separatrix curves divide motion types. Trajectories move away from theta is equal to pi unstable. Demonstrates periodic and chaotic like behavior in nonlinear systems. Next, energy interpretation. Energy interpretation is total energy E is equal to K plus U, E is equal to K plus U, E is equal to K plus U. For small energy, oscillation around stable point. For energy equals to separatrix, pendulum reaches vertical. For higher energy, continuous rotation, phase plane and energy diagrams correlate with the stability. Correlate with the stability. We are going to see applications. The applications are robotics, engineering, vibrations and control systems, magnetic modeling, nonlinear dynamic analysis, and stability of mechanical structure. The applications of the are robotics means balancing systems, engineering vibrations, control systems, and mathematical modeling, nonlinear dynamic analysis, stability of mechanical structures. And coming to final conclusion, pendulum governed by the nonlinear differential equations means the pendulum is differential by and considered by the nonlinear differential equations. Second point, equilibrium points at theta is equal to 0 and stable and theta is equal to pi are unstable. Matrices. Jacobian and eigenvalues help classify stability. Matrices of Jacobian and eigenvalues are very helpful to classify and stability. Phase plane offers a powerful visual tools, combines calculus plus in linear algebra, nonlinear dynamics. Means the phase plane of offers visual tool. The phase plane will also offer the powerful visual tool and combines calculus plus linear algebraic nonlinear dynamics. Means it combines with the calculus and linear algebraic plus nonlinear dynamics. Thank you.